Now that you have your lab open, you're ready to start working on it, go ahead and open the file that I've provided for you for this lab, the Conservation Mechanical Energy Virtual Lab. Now it goes through step by step, so we're going to look at each of these steps. We're on step number 3. Measure the initial location of the spring relative to the ground using the ruler on the left-hand side. Okay, so we're going to take this ruler and we're going to move it and we're going to put it right underneath that spring. And it's kind of hard to see. Let me kind of move these around. This ruler, we're going to use the bottom of the screen as kind of our ground. Okay, so we've got 10, 20, 30, 40, 50, and then 60 centimeters for our initial distance. That's how high the spring is up when it doesn't have anything hanging on it at all. Right? I also want to switch this friction to none. Right? So let's go ahead and look back at our form here. And it tells us the initial distance is going to be 60 centimeters, but I have to convert everything to meters. So that means that I have to divide 60 by 100, and that's going to give me 0.6 meters. Step 4, pick up a 50-gram weight by clicking on it and hang it on one of the springs. Measure the distance from the dotted line to the bottom of the spring and record your measurement in the column labeled stretched spring. And we also have to record this in kilograms. Okay, so let's go back to our lab. We're going to take this and put this on there. Now, I'm going to kind of click on it to get it to stop. And even though it's oscillating a little bit there, you can see that it's to the 5. We can pause it. Okay, see how it's at 5 centimeters. Okay, so that's what I'm going to record for the stretch of my spring, and I'm also going to record the mass. Now I have to do 50 grams divided by 1,000 to get kilograms, so that's going to give me a mass of 0.05 kilograms. The stretch of my spring is 5 centimeters, but I have to make that into meters. So the stretch of my spring is going to be 0.05 meters. All right, and that will be repeated with each of the weights that you have there. Okay, now it says replace the mass with the 50 gram. Of course, we're not doing the others. With the mass on the spring, raise it up to the dotted line and then release it. Watch the spring closely to find the high and low points of the oscillation. So I'm going to take and squish this up. And now this is where it's handy to slow this down. See, if I let go of it, oops, I have it at paused. See how I have it paused so it's not going to move? I'm going to slow this down so I can see its oscillation. Where's its low point? It got down to 9 is what it looked like to me. Let's see. 9 centimeters is what that looks like to me. So let's go back and we are going to log this in as 9 centimeters? No, 0.09 meters. Oops, that was my low point. Okay, my high point is going to be 0 because that's where it was up at the very top. All right? So at the highest point, it's at 0. At its lowest point, it's at 9. You're going to repeat that for all the masses. Now we go to table 2. Okay, now we're going to be looking at force. In order to find the force, you have to convert your mass to newtons. All right? Remember that force is equal to mass times acceleration. When we're talking about the force of gravity, we're talking about acceleration due to gravity. And so our force is going to be the mass of the object in kilograms times 9.81. So in the case of my first thing here, I've got 0.05 clear all this out of here. Okay, I've got 0.05 for my mass times 9.81. So the force of gravity, or the weight, if you will, of this weight here that's bouncing up and down for us is equal to, oops, come back here calculator, 0.49 newtons. Now, after you find the force for each of them, you're going to need to calculate the spring constant. And I give you the formula here for the spring constant. It is force divided by the stretched spring. Okay, the force divided by the stretched spring. The stretched spring is going to be my stretch at the very beginning up there, 0.05 meters. Okay, so let's take a look at this one. We're going to do 0.49, that's my force, divided by the stretch of my spring, because what the spring constant is telling us how stretchy the spring is. So my spring constant is 9.8. The next thing we're going to do is calculate the elastic potential energy at the high point and the elastic potential energy at the low point. The formula is provided in number 2. The potential energy elastic is equal to 1/2 K, our spring constant, times the displacement squared. Okay, so we're going to be looking at the displacement of our object, okay? So for the high point, let's go back here. High point, it was 0. So, well, you can see that 0 squared is going to be 0 times k is going to be 0 times 1/2 is going to be 0. So our elastic potential at our highest point is just going to be 0. What about our potential energy at our lowest point? Now here we have a stretch to our spring, don't we? We've got 0.09 meters. So we've got 1/2, I'm going to just put 0.5 in there, times K, which is my spring constant, 9.8, times the square of my displacement. And so my elastic potential energy, come back here, little calculator. My elastic potential energy is 0.3969. We could probably round that up to 4 joules. This one's going to be no joules. All right. All right, so you're going to do the same thing for all of your different masses. The next table asks you to find the potential energy, but this time it's the gravitational potential energy. All right, so we are going to be looking at the high point and the low point, because if you remember from your lesson, the gravitational potential energy has to do with position. Okay, so let's take a look at where this little fellow is as he's bouncing up and down here. What's his position? We're just going to use the top of the mass. What's the position of this thing at its high point? Okay, now we're measuring from the bottom. So at the high point, it's 60 centimeters from the ground. You see what I mean? So we've got 60 centimeters from the ground. So the highest point is going to be 0.6 meters. Its lowest point is that Remember it went down 9 centimeters? See it going there? So we have to do 60 minus 9 to get 51, but we have to convert that to meters, 51.51 meters. Okay? So we calculate the potential energy by doing the mass times gravity times the height that it achieves. Okay? So the potential energy, let's calculate the potential energy of this. The mass of my object in kilograms, 0.05, times 9.81, times the height. Okay, so my highest point is 0.6. And there's my potential energy at the highest point. So 0.2943 joules. Now for the lowest point, I do 0.05, 0.05. Oops, I was typing the wrong thing. Calculator works better if I put it in the right place. Let's start this over again. Okay, 0.05 times 9.81 times 0.51. And as I suspected, my potential energy is less when it goes down to the ground there. And I don't need all those decimal places because I really can't even have that many using significant figures. All right. So now the very last one is we're going to be looking at the total potential energy for each of these. Okay, so I'm taking my elastic potential energy at my highest point and my gravitational potential energy at my highest point, and I'm adding those together to get my total potential energy, the combination of both of those. So obviously the first one's 0, so this is going to be 0.29, and we can just leave it. We're just going to round it off to that, joules. But what's my total potential energy at the bottom? All right, well, I've got 0.05 at my lowest point and 0.25, so I've got to add those together, 0.04 plus 0.2502, and I get 0.29 joules. Exactly the same top and bottom. What does that tell you about conservation of energy? Now let's take a look at this. There's another little thing that you can see that I hid. Couldn't remember. All right. Watch the energy as it changes. The elastic potential energy and the gravitational potential energy. We also have some kinetic energy in there, movement that goes into it as the thing's actually falling. I hope this helped clarify this lab for you. It can look a little tricky, but just follow these steps and you'll have it finished. Remember to turn the friction off, slow down your speed, and most of all, remember to convert your units to meters and kilograms. Enjoy your lab. Bye.